안녕하십니까. 고려대학교 정경대 학장 구교준입니다. 반갑습니다. 더 강한 고려대학교의 2025년 개교 120주년을 기념하여 인류사회의 발전에 기여한 명사를 모시고 진행하는 넥스트 인텔리전스 포럼이 벌써 6회를 맞이하였습니다. 이번 포럼은 우리나라 사회과학 연구를 선도하는 고려대학교 정경대학의 설립 70주년과 경제학과 창과 120주년을 기념하기 위하여 2011년 노벨 경제학상 수상자이신 토머스 사전트 교수님을 모셨습니다. 본 강연을 통해 고려대학교 구성원들의 우리가 살고 있는 세상에 대해 연구하는 사회과학에 대한 관심과 이해의 지평이 넓어지기를 기대하겠습니다. 다음은 김동원 고려대학교 총장님의 인사 말씀이 있겠습니다. 총장님을 앞으로 모시겠습니다. 큰 박수 부탁드립니다.
존경하는 토마스 사전트 교수님, 그리고 오늘 이 자리에 함께해 주신 귀빈 여러분, 학생 여러분, 많은 연구자 여러분, 반갑습니다. 오늘 먼저 뜻깊은 강연을 해주실 토마스 사전트 교수님께 존경과 감사의 말씀을 드립니다. 아울러 고려대학교 제6회 넥스트 인텔리전스 포럼에 오신 모든 분께 환영 인사를 드립니다. 넥스트 인텔리전스 포럼은 우리 학교 120주년을 기념하는 이 석학들을 모신 이런 포럼인데, 그동안 쭉 진행을 하면서 지난 5번 동안 계속 자연계 쪽에 석학들을 모시게 됐습니다. 그래서 이번에 인문계 쪽에 우리가 계속 훌륭한 분을 모시려고 노력을 하다가 드디어 사전트 교수님을 모시게 되어서 아주 기쁘게 생각을 합니다. 고려대학교는 내년 2025년에 개교 120주년을 맞이합니다. 한국 최초의 근대적 고등교육기관으로 설립된 고려대학교는 지난 역사를 통해 수많은 기라성 같은 인재를 배출하며 대한민국의 산업화, 민주화, 세계화에 혁혁한 기여를 해왔습니다. 민족의 대학으로서 자랑스러운 역사를 쌓아온 고려대학교는 이제 개교 120주년을 계기로 세계를 무대로 인류의 미래사회에 공헌하는 대학으로 한 단계 더 높게 도약하고자 합니다. 이에 인류사회와 세계 발전에 이바지한 분들을 모시고 강연을 듣는 넥스트 인텔리전스 포럼을 지난해부터 진행해 왔습니다. 오늘 우리에게 강연을 해주실 토마스 사전트 교수님은 거시경제학 분야에서 탁월한 연구 업적을 쌓음으로써 인류의 지식 발전에 크게 기여하신 공로로 2011년 노벨 경제학상을 수상하신 분입니다. 사전트 교수님은 오늘 인공지능의 근원을 주제로 강연을 해줄 예정입니다. 교수님께서는 과거 다양한 과학혁명의 역사를 통해 생물학, 통계학, 물리학을 중심으로 인공지능이 어떻게 발전해 왔는지를 살펴보고 인간의 제한된 인지 능력과 그 한계가 갖는 경제학적인 의미에 대해서 우리에게 말씀해 주실 것입니다. 우리가 AI에 대해서 많은 그 IT라든가 컴퓨터 쪽에서 얘기를 들어왔지만 경제학적인 시각에서 듣는 건 참 드문 일인데 오늘 아주 귀중한 기회를 얻었다고 하겠습니다. 오늘 사전트 교수님의 강연을 통해 우리가 살아갈 인공지능의 시대를 이해하고 미래사회를 준비하는 데 필요한 지혜와 통찰을 얻기를 기대합니다. 이번 제6회 넥스트 인텔리전스 포럼은 내년에 맞이할 정경대학 70주년 또 경제학과 120주년을 함께 기념하는 의미를 갖습니다. 한국사회과학 연구의 본산 고려대학교 정경대학은 1955년 정경학부로 출발해 오늘에 이르렀으며 경제학과는 1905년 고려대학교 설립과 함께 이제학과라는 이름으로 당시 시작되어 내년에 120주년을 맞이하게 됩니다. 오늘 이 포럼이 많은 우리 연구자들에게 영감을 주고 또 많은 학생들에게 지적인 호기심을 더 끌어올려서 훌륭한 연구자로 성장하는 계기가 되기를 바랍니다. 다시 한번 이 뜻깊은 자리에 함께해 주신 모든 분께 감사드립니다. 이번 포럼이 우리 고려대학교가 민족을 넘어 인류사회에 공헌하는 학문의 전당으로 발전하는 데 소중한 의미를 갖기를 기대합니다. 감사합니다.
네, 총장님의 따뜻한 환영사 감사드립니다. 이어서 오늘 강연해 주실 토마스 사전트 교수님을 소개해 드리겠습니다. 교수님은 미국의 경제학자로 1968년 하버드 대학교 경제학 박사학위를 취득하셨습니다. 1997년 어윈 플레인 네머스 경제학상을 수상하셨고 2011년에는 거시경제에서 원인과 결과에 대한 경험적 연구로 크리스토퍼 심스 교수님과 함께 노벨 경제학상을 공동으로 수상하셨습니다. 교수님의 대표적인 업적은 합리적 기대 가설을 바탕으로 정부 혹은 중앙은행 정책의 인과관계를 연구한 것입니다. 가계나 기업 등의 경제 주체는 경제 상황의 변화를 합리적으로 예측하여 행동하기 때문에 정부의 재정 금융 정책이나 중앙은행의 통화 정책이 시행되더라도 그 효과를 분석하고 평가하기 어렵습니다. 이는 경제 주체들이 정책 변화를 예측하고 그에 맞추어 미리 대응하기 때문입니다. 교수님께서는 이러한 합리적 기대를 고려한 새로운 거시경제 모형을 개발하여 정책의 효과를 분석할 수 있는 방법론을 제시하셨습니다. 이 방법론은 오늘날에도 거시경제 분석과 정책 평가에서 중요한 역할을 하고 있습니다. 자, 이제 토마스 서전트 교수님을 모시고 오늘 강연을 청하겠습니다. Professor Sargent, the floor is yours.
I'm sorry I have to speak English, but I actually barely speak English. So I'm going to talk about the origins of artificial intelligence. I'm going to go slowly, and I'm going to define words. So before I talk about artificial intelligence, I have to define intelligence. So I'm going to think of intelligence in terms of activities, actions. Oh, by the way, ask me questions and disagree with me. So I'm thinking about human intelligence. By the way, this could not only be humans, it could be certain kinds of animals. With human intelligence, there's three things that I think intelligence people do, activities. First, they recognize patterns. They recognize patterns. Recognizing patterns is like forgetting things and abstracting things. It's like taking a huge amount of data, ignoring lots of things, and compressing the data into a few patterns. So we do that all the time. Second thing is, after we detect a pattern, we generalize. So on the basis of our experience, we see some patterns somehow, and then we think those patterns are going to hold up in new situations. That's generalize. It's a bold thing. And then the last thing we do, on the basis of those first two things, is we make decisions. We decide to go left. We make choices. We decide to go left or right. And we do all those things all the time. And when someone does those well, we say they're intelligent. So that's what I mean by intelligence. That's what I mean by human intelligence. I'm almost done with my entire talk. So now you could ask, what do I mean by artificial intelligence? Artificial intelligence, I mean, it's a machine that does at least one of those three things. That's what I mean. It could be a computer, okay, and so on. Okay, so now I'm gonna tell you something I read from a cognitive psychologist named Steven Pinker. he wrote a book called The Blank Slate. And if you're a junior high school student or a high school student or a college freshman, I would read this chapter. Because this chapter gives his theory or opinion about what we should study in school, things that we should learn. And here's his philosophy. The purpose of school is to teach us things that we're not naturally inclined to do. And so he's a cognitive psychologist. He says the purpose of education in modern life is to overcome our cognitive disabilities. We all have cognitive disabilities. And those cognitive disabilities are the ability to do those things on the first, to be intelligent. Okay, I have serious cognitive disabilities, learning disabilities, but we all do. So what he says is, because of evolution, we are like we are because of tens and hundreds of thousands of years of biological evolution. And, we came from other animals or plants, depending on how you count, maybe 2.5 billion years it took, and here we are today. We evolved through this process that was basically survival of the fittest. And it equipped us for most of the time that we were human beings. We've been human beings like maybe only 100,000 or 150,000 years ago, maybe less, maybe 60,000, meaning we looked like we do now and we could talk. We could talk. So most of the time we did that, we evolved to be hunter-gatherers. Okay? That's what we are, nature equipped us to do. Okay? So what he says is, as a consequence, we were taught to do some things very well. We're very good at doing some things that were useful when we were hunter-gatherers. Like, I don't know, if you play soccer, you do lots of things that, I don't know what sports you play, but if you play soccer, I know you play baseball. I went to a baseball game. You're using skills that are for hunter-gatherers. Okay. But he says there's 4 things that we're really bad at. And what they are these 4. Actually, he says 3. I've added the 4th, physics. Okay. In honesty. But I'm sure he'd agree with me with physics. So what's statistics? What's statistics? Statistics is understanding relative frequencies of various events. That's what statistics is. It's about relative frequencies. You could call them probabilities. But all the probability is a fraction of time something happened. And we're good at certain, as hunter-gatherers, we're good at certain kinds of fractions. We're really bad at others. And he says in particular, we're bad at dealing with events that occur with low probability. We weren't bred for that. So I spend a lot of time in the mountains watching animals and stuff. And there's some things that we naturally do. There's some things that, but it has nothing to do with a lot of things we have to do in modern life. So he says we're naturally bad at that. So that's and it's not just because of the cognitive disabilities I have. You have them too. The next field is biology. So what's biology? It's so we are naturally we're evolved to have theories of biology. What's biology about? It's about birth and death and life and the origins of those things. And we, we evolved to have certain theories of biology. And in terms of it's okay for hunter-gatherers, it's terrible for making decisions about modern life. We're just not good at it. And our instincts are about birth and death and life. What our instincts are, the thing we're bred, that we do naturally. We're bad at it. What's the next thing? Economics. So what's economics about? Just back up. It's about production, distribution, trading, and exchange. And he said, you know, hunter-gatherers, we evolved to have certain primitive rules about economics. And those rules don't equip us to do with things that we have to do in modern life. For example, theories of, in modern life, intermediaries are playing a role. They don't produce anything. They stand in between buyers and sellers. They're in distribution networks, and they don't produce anything. They're parasites. So what he says is our natural theory of economics is very bad and has caused societies to make very bad decisions over and over again, like pogroms against minorities who are intermediaries, middlemen. And then the final thing is physics. So what's physics about? It's about stuff, matter. It's about movement over time. It's about light and space. And we have natural theories of those things. And they're great for hunter-gatherers. They're terrible for modern life. Okay. So what Steven Pinker says, the task of, and in modern life, in all of those areas, many of the things that we as individuals or as societies have to do relies on being sophisticated about those things that we're really naturally bad at. So what Steven Pinker says in this chapter, the chapter is a great title. It says, Out of Our Depth. Out of our depth. He says the purpose of education, designing an education, is to learn things that will compensate for our cognitive disabilities, the particular cognitive disabilities that we need to make wise decisions today. So that's what he says. Okay. So now what I'm going to do, those are our cognitive disabilities. The next slide is going to be the technical tools, the subjects that are the backbone of artificial intelligence. So what is artificial intelligence? It's how we human beings create machines to do those three activities that I talked about. Okay, so here's those, oh, oops, yikes. Okay, look at that slide, look at the title. Look at, damn. Those are the sources of artificial intelligence and machine learning. Those are the tools. So what are they? Statistics, biology, economics, and physics. And I submit, you know, it's not original with me, that if you want to go underneath the hood of artificial intelligence and machine learning, it's some mixture of those four things. And here's you know, economics and what we study, what we're privileged to study, is beautiful because it's full, in a whole bunch of ways, it's full of ironies. Because the same things that we need to make artificial intelligence are things we're naturally good at. And I have dyslexia, and I usually say things backwards, but I meant that. Okay, so, and I'm going to deliver on this, okay? So now I'm just going to give you, some examples of people who have been doing artificial intelligence for a long time. And, but not that long. That's one of the things, not that long. It's something we didn't start to do well until fairly recently. You know, like, I'm old. But maybe 4 or 5 lifetimes of my length, that's when we started doing this as human beings. It's kind of a miracle. So here's what I'm going to do. I'm going to push this once. Here's the authors of the scientific revolution. This started, I submit that machine learning and artificial intelligence started with the what's called the scientific revolution. And that starts about 1550 or 1600. So I'm going to give you some examples and tell you what they did. I'm an economist, and actually I'm a macroeconomist, and I love monetary theory. I like theories of money. And I've put red little things for people who were monetary economists. And I could say amateur monetary economists. No, it was a serious part of their work. They did famous things. So the authors I'm going to talk about are Copernicus, Tycho Brahe, Kepler, Galileo, Newton, and Darwin. And actually, Darwin didn't say he was an economist, but he got a key idea from economics. He read economics. He read Adam Smith and Thomas Malthus, and he used it. Okay, so I'll talk about it. So I'm just going to tell you what they did. I'm going to draw some graphs with my hands. Okay, so here's what Nicholas Copernicus did. So if you ask, what does machine learning do? What does machine learning do? If you kind of ask. And you know, ChatGPT, have you heard of that? That's what this does. What it does is it fits functions to data. It fits curves to data. It runs regressions. You with me? That's what it does. So it has some data. It's a big mess, and what it does is it wants to describe that. What does it want to do? It wants to recognize a pattern in this data. It's going to do pattern recognition that it's hopefully going to use to generalize. So what it does, here's a big mess. It fits a polynomial. You know, we used to call it a polynomial. Now we call it a deep neural net. But that's all it's doing. Okay, so that's what it's doing. And why is it doing that? So why is it doing that? So think about it. You have this big mess of data, big scatter. It's all over. You want to see a pattern in it. Another way to say that is you're going to ignore stuff, or you're going to compress it. All those words, or you're going to reduce it. So that's what pattern recognition is. So here's what Copernicus did. He had some observations and a theory about how locations of planets at various dates. That's what he had. And you know, when we started being intelligent, in some sense, people looked up at the stars and the skies, and they noticed some things. They noticed most of the stars just stay where they are, but there's a few that wander, planets. So for several thousand years, people started making tables of where particular planets, there's 5 or 6 are, these wanderers, where they were at each time. And they noticed it kind of cycled. Okay, so the Greeks started doing this in various ways, and the most successful, I could have put him up here, he was Ptolemy. Greek that lived in Alexandria in Egypt about 2,000 years ago. He made a model, and he fit some curves. And I don't know if you take statistics, he actually was fitting some Fourier transforms. He was fitting some circles. So what he did is he got this model with epicycles. It was a model with a bunch of parameters. So what it is, it's this mess of data. So think what he has. He has, going back to the Sumerians and the Greeks and the Romans, he's got these measures of where the planets were. And he took them and he reduced them to a very small system called epicycles. So he had the sun in the center, and then he had the Earth and the various planets going. No, I got it wrong. He had the Earth in the middle. He has the Earth in the middle, and then he has everything else, the sun and the moon. They're all going around us. All the planets are going around us. So he insists on writing down a model, a statistical model that has that feature, and then he's going to jiggle the coefficients to fit it. So that's what he was doing. And he got this model with lots of parameters. Lots of parameters. It actually fit really well. Okay. So, and it's got, I don't know how many parameters. Let's say it has 300 parameters. That's a lot of parameters. And it's kind of ugly. You could say it's got these circles, and then it's got circles moving around the circles, and it's got lots of parameters. So when I say it's ugly, my wife's a guide in a museum. She says, in a museum, you're never supposed to say ugly or pretty or beautiful. But Copernicus did. He said that's ugly. Why? It's got too many parameters. So what he said is, I think I can explain the same data with fewer parameters. So what's he in the business? He's in the business of reducing the dimension of the curves that he's going to use to fit the data. So what he does is he says he makes one change. He's going to use circles. He loves circles. Why? Because Plato and Aristotle said circles are great. And they are, like they're kind of perfect. They're completely symmetric. So it's kind of an aesthetic thing. You know, if God's going to make things, it's going to make them really beautiful. So he has circles, but what he does, he makes one decision. Instead of having the Earth being the center, he says the sun's the center. He does that. And then guess what? Instead of having 300 parameters to fit to the curves, he's got 10. And he fits it. Okay, now I'm going to come back to beauty again. So he terribly reduced it, and he got a pretty good model. It did not fit as well as Ptolemy's. And now he does something which scientists do to this day. He says his model is better, not because it fits better. It's got fewer parameters, and it's prettier. Scientists do that all the time. Physicists do it. So he did it. So what he was doing machine learning by hand. He was fitting the curve. Okay. So now, who's the second guy? Oh, Copernicus was also a monetary economist, and he discovered something important. But this isn't a talk about monetary economics. But I actually think the fact that he was a monetary economist helped him as an astronomer. And I'm not kidding. Okay, so now we go to Tycho Brahe. So who was he? Big data. He was a big data guy. He measured stuff. And what he did is he got more accurate measurements, and he made a huge data set of the location of the planets. And then what he did is he did the following. So he was a big data guy, but not an artist. So what he said is, I can beat Copernicus's model by making something that's uglier. So instead of having 20 parameters, he went back up halfway to Ptolemy. And he got a better fit. But it's uglier. So guess what? Scientists, it's not that difference between a scientist and an artist. And famous scientists will tell you that. Okay, so now we come to Kepler. Okay, and what Kepler did was, it's kind of the height of, there's a big lesson about machine learning here. What Kepler did is, he worked for Brahe. So guess what? We do this all the time. He worked for Tycho Brahe, and he was more of a theorist and more of an artist, and he had more data than Copernicus or Ptolemy did because he had Brahe's table. So what he has, a huge table. It's a big table, and it's got locations of planets. And what he says is, I'm going to fit a simple model that fits better than Copernicus's model. And he works on this for 20 years. He does machine learning for 20 years. And now think what he's doing. He's going to change functional forms. He wants to keep the number of parameters small. And what he does is he's going to use very simple math. And the math he learned from Euclid. He learned from Euclid. Geometry. So what he's going to do is instead of saying, why circles? Why not an ellipse? So he puts the sun in the middle, but instead of having planets be circles, he had to be ellipses. And guess what? Just that change makes it fit much better. And then he got this fast. He ended up getting Kepler's 3 laws, which is a very economical, low-dimensional pattern recognition, huge extraction. He took a huge number of tables and reduced them to just a few parameters. So go look up at Kepler's 3 laws. There's essentially 3 parameters. One of them's 2, one of them's 3, and one of them's k. And they describe the motions of the planets. And look at that, and it's beautiful. Okay. So go look at that tonight. Actually, I have a slide on it because it's so beautiful. Okay, that's what Kepler did. Now we have Galileo. Galileo, he was an artist in machine learning and data generation. Because notice, those first 3 are astronomers, which means they're like economists, because macroeconomists don't get to do experiments with their economy. Actually, you do not want to live in a country where a macroeconomist is doing an experiment. You just don't want to. So astronomers don't get to do experiments. But Galileo was interested in things where he could do an experiment. So here's what he did. Okay. He challenged authority, and he challenged the church. So Aristotle had said the following. You take a great big heavy ball, and you take a light ball, and you drop them, and ask a 7-year-old who doesn't have, ask a 7-year-old this who hasn't had a science class. He or she will tell you the big heavy ball is going to hit the ground sooner than the little ball. That's what Aristotle said. And that had been believed for over 2,000 years because Aristotle said it. And what Galileo said is, this is the beginning of science. He said, well, that's a theory. Can I check it out? And why not check it out? So he could say, well, I could drop 2 balls, but actually they fall so fast I can't really. So what he did is he said, I'm gonna slow down how fast the balls go. So this is simple and ingenious. So what he did is he's going to make here's my graph. He's going to take an inclined plane. So look what he's doing. He's going to take an inclined plane, and he's going to make a groove in it, and he's going to put a ball here of a certain size, and he's going to let it roll down. And remember, in those days, he didn't have much of a clock. Well, actually, you have a clock, and I do. It's our pulse, a crude pulse. So what he's going to do is he's going to roll the ball down, okay, and then he's going to start it here, and he's going to see how long it takes to hit here, here, here. Then he's going to take a heavier ball, do the same thing, and he's going to make a big table. He's going to make a big table of data. Now notice the following. God generated Brahe's table of the planets, but Galileo's generating this. And so all he can do is he can change the angle. That's what he did. That's his inclined plane. And then what he fits a function. And then so he fit a quadratic function. Linear function didn't work so well. And what he discovered is the law of constant acceleration. No matter what an invariant, no matter what, there's a quadratic relationship between distance and time that was independent of the weight of the ball. So he discovered something key, the law of constant acceleration. It starts at 0 and then it accelerates at a constant rate. So acceleration is a second derivative, so it's quadratic. And how did he do that? He didn't need a cubic. He didn't need a deep neural net. He needed a polynomial of second order. So that's what he discovered. That's look what that's data generation, and it's running a regression. Okay, so that's what he did. Okay, so now here's the following, and this is going to come up. Okay, we're going to get the essential challenge of machine learning, and it's about the promise of machine learning. They were doing machine learning, and they discovered something that was invariant, that law of constant acceleration, the laws of the planets, and they discovered this pattern. And now here's what they didn't. Here's what they didn't do or claim to do. Why is the pattern like that? Why is it? What's going on? What's generating it? And they said, I don't know, that's just what the pattern is. But the next person, he wanted to go beyond that. And that's Isaac Newton. And what he wanted significantly to take Galileo's observations about acceleration and Kepler's observations and unify them under one theory. And so he got what economists would call a structural theory, where he got his laws of gravitation, the inverse square law, which said think about what the leap is. You learn this in high school or junior high school, that the same laws of acceleration that are governing the falling, it's not true that Galileo dropped the ball from the Tower of Pisa, because that wouldn't have worked. He did this. That same law governs the motion of the moon around us. Because there's an acceleration, because the moon's falling toward us. So the moon's falling too, just like this. And it's governing the same law. And you could say, is this pattern recognition or generalization or explanation? But it goes well beyond what Kepler did. So he exercised some theory and got this inverse square law for gravity. And that's how he discovered that. Okay, so now in machine learning today, machine learning is very good at doing the Kepler stage. most of it doesn't even try the Newton stage. Okay, so when people are talking about is artificial intelligence and machine learning going to replace jobs, you should be concerned about this. Is it going to replace jobs or create jobs? So it's kind of interesting whether it can do things like Kepler. It does that very well. Doesn't get close to doing things like Newton. And you're going to be thinking about that in your life. Now, who's the next one? Charles Darwin. Okay. So Charles Darwin was a machine learner. What do I mean by that? He didn't use math, and he didn't have a lot of theory. He had very little theory. So here's what Charles Darwin has. He's a collector of a data set. So he's a person that studies animals and plants. And he writes down a bunch of data on animals and plants. That's what he does, varieties. It's a huge mess of data, and he stares at them. Okay. And he notices some things. By eye, he notices some patterns. So that's one thing. So he notices some patterns, and one thing you have to know is he had a hobby, raising pigeons, breeding pigeons. He bred pigeons, and what he noticed is, what do pigeon breeders do? They take some pigeon characteristics that they like, these pigeons, and they get two pigeons to fall in love, and they have babies that look somewhat like the parents, and then he does it again and again and gets a pigeon with a different color that he likes. So what he noticed from that is pigeons, baby pigeons tend to look like their parents. First thing is, so there's some inheritance, but second is they don't look exactly like their parents. There's some variation. So he has inheritance of some characteristics. It's just an empirical thing. He has no idea why. I'm not even sure he knows what a cell is. He doesn't know what DNA is. He doesn't know what a gene is. He just sees that. And then the second thing he says, well, how do I get new varieties of pigeons? It's selection by Charles Darwin. It's selection by Charles Darwin. I select them. I'm a marriage maker. I'm a matchmaker. That's what I do, and I select. Okay. So then, I keep the ones I like. It's very cruel. I eat the ones that I don't like. Okay. So now, he's saying yeah, but in nature, what he also notes in nature, he goes to Galapagos Islands. He sees a bunch of birds, and they remind him of other birds, but they're distinct species. And in those days, here's what he's after. The ruling theory is that God made all the species. Darwin's suspicious, but he doesn't. Okay, so he says, I have these two principles, inheritance of characteristics and natural variation, but I don't know about selection. And then what he's doing is he reads some economics. He reads Malthus. And Malthus he's an economist. He has a theory about how there's too many babies born, human babies, and what happens is there's more babies than there's food, and a bunch of them die. And so Darwin reads this, and he says, this is my missing principle. Who does the selection? Nature. It's evolution by natural selection. That's his third principle. And if you read the Origin of Species, which you should read, in the introduction he thanks Malthus. Another person he read was Adam Smith, who had theories of evolution a long time, 80 years before. So economics was used. Okay, so he was doing lots of pattern recognition and almost no theory. And what he discovered was something that it wasn't accepted at first. It wasn't accepted until the early 1900s. But he discovered something just from data recognition. Okay, so now what I'm going to do is I'm going to show you, I'm going to look under the hood of AI. I'm going to do this in 2 steps. Okay. So here's the thing. So I don't know if you've heard of AlphaGo, which is it's a product. Google owns it now because they bought it. It's a computer program that beat the best Go player in the world, which is very hard to do. IBM couldn't do it. And what they did is, I'll tell you more about what they did was, they copied somebody who I actually met. It was, I'll tell you about it. I'm going to tell you I'm going to tell you the ingredients that AlphaGo used and where they got their methods. It's like cooking. Go watch a YouTube video on what they did. It uses the following combinations. It uses prices and values. Prices and values are appearing. So all over artificial intelligence. Game theory. That's from economics. I'll come back to that. It uses distributed computing, which is from statistics, physics, and computer science. It uses dynamic programming, which is from economics and applied math. It uses Monte Carlo simulations, which is from statistics. It was invented from my father-in-law's thesis advisor, who's a physicist, to build a thermonuclear bomb, Edward Teller. And it uses competition and survival of the fittest from Darwin. It uses all of those things. And those are the ingredients of AlphaGo. So an early predecessor of AlphaGo was this person named John Holland. I met him in the mid-1980s. He was a computer scientist, a philosopher, and a psychologist all at one. He was combining all of those things. And what he wanted to do was build an artificial brain that would make decisions. So it's going to do all the things that I talked about. So here's how he did this. He built the Holland classifier system, or also something called the genetic algorithm. He invented the genetic algorithm. If you kind of fast forward, it's a way of finding the maximum of a very hard to find, a maximum of a very difficult function. You can't do it with calculus because it looks like this. It looks like that. And he invented this genetic algorithm. Fast forward. The genetic algorithm was used by Meyer, the one who discovered exoplanets, to do maximum likelihood estimation of his model to discover exoplanets about in the 90s. So here's what he does. Here's what Holland's model of the brain is. What the brain is it's a bunch of if-then statements that look like DNA. So what it is, what's a statement? It's got an if and a then. And you take a binary string of zeros and ones, and the first part of the string is the if part, the second part's the then. So an if might be, you meet somebody. Okay, so here's an if. I meet somebody. Here's a then. So the if is I meet a friend. The then part is hit him in the face. The second part is, if is then is turn around, turn your back on him and walk away. The third string is, say hello, and so on. The if then. So your brain is full of all these if thens. His artificial brain is full of these things. And then what he has is, he has a way of changing these strings. And the way he does it is with, from biology, mutation. He's encoded these binary strings with zeros and ones. A mutation is a zero randomly flips to a one and a one to a zero. That's mutation. The other is sexual reproduction. What's that? And this is very romantic. You read his thing. So you take two strings. You randomly match two strings. You call them the happy couple. Okay, then what you do is you randomly divide them in two. Okay, you divide them, you split them, and you take this part of this string and you put it on this one, and this part of this thing and this. And that's called, actually, he got this from biology. That's what happens. And so he turns on both of those. So what's happening in his computer algorithm is this is going on. There's all these if-then statements competing. So think of my mind. I get into a situation, I have all these strings. It's kind of true. There's a whole bunch of things you can do. Okay, then what he has ledgers. Ledgers, where do those come up with? Cryptocurrency. What is Bitcoin is just a big ledger. It's just a record of. So there's a ledger where each of these little strings has an account. Well, what do I mean by an account is, okay, the string, so somehow I use the string, okay, turns out for a string, all the strings that I have in a given situation, they have to compete for the right to make a decision. So guess what? He holds an auction. There's an auction, economics. And the one who pays the most makes a decision, in my mind. Okay, if it's a good decision, its bank balance goes up on its ledger. If it's a bad decision. Now, what do you mean by good or bad? You try it out. I see you, you see me, and you hit me. You get penalized for that. Okay, and so on. So it keeps on. So there's competing if-then statements, there's auctions, there's randomization, and there's a trade-off between exploration and exploitation. Those are all the elements that he puts together, and he builds this machine. They've been used in economics to solve problems that the best economic theorists couldn't solve. Okay, and they found exoplanets. So he did that in the 80s. Now let's fast forward. Okay, so now if you kind of look at AlphaGo, it's a modern version of that. Okay, so the point is, what you're supposed to see for this, there's economics all over there. Okay, so now I'm going to go further. How am I doing in time? Okay, good. Okay, this is good. Okay, so now I'm going to talk about. This is going to be, we kind of think about, so so the whole point is this artificial brain was making decisions, just like AlphaGo. So what you're supposed to get from this is using everything. This is using all of those things that we're cognitively disabled on. It's beautiful, and the irony is beautiful. Okay. It makes no sense that we're making machines to do some things better than we are, and the tools we're using are things we're not good at. But a few of us are better at some things than any of these machines are. And there's these giants, I'm going to mention, von Neumann and Morgenstern, and Koopmans and Marshak. The first three, Lucas just died, very sadly. But the first three are the giants of who created modern economics. Von Neumann and Morgenstern created game theory, the theory of games, and Koopmans and Marshak created simultaneous equations, modern econometrics, which was at the frontier. It's still way beyond the frontier of some work. And the interesting thing is, if you read the introduction to von Neumann and Morgenstern, and you read Koopman's key paper, when they describe what they're doing, they mention the following people. They mention Kepler and Newton. And what they say is, and they both say very similar things. They say there's the Kepler stage, which is curve fitting, pattern recognition, curve fitting with no explanation. And then they say there's a Newton stage where you try to make progress on why. Okay. And kind of like the delicate thing is, von Neumann knew this. So how much further did Newton get than Kepler in terms of why? So he thought he got a lot farther, but Einstein got even farther. And there's guys who've gotten even farther than Einstein. So what I mean, gravity. So Newton had a theory of gravity which worked well, but it was a bluff. I mean, a bluff, action at a distance, that square law. And that's not modern. A modern physicist says that wasn't really why. You know what I mean? So he rolled back where the why is. Okay. So now here's where there's a role for, according to both von Neumann and Morgenstern and Koopmans and Marshak, the Newton stage is a lot harder. And that's what some of us, when I say some of us, and I mean von Neumann and Morgenstern, I'll come back to that, they're good at pushing it back. Maybe the rest of us, me, I'm kind of back with the Kepler stage at best. Okay, so now I want to tell you about the following. Let me go back. Okay, so here's. Okay, so ask the following thing. So you can hold your head up. I don't know if you have this problem. Do you ever have this problem? You're an economist, and you go to a party, or you see your parents or your uncle, and they ask you what you're doing as an economist. And they ask you things, well, you're an economist. What's going to happen to interest rates tomorrow? That's what they think that we do. And like, it's very hard. My wife told me I'm so bad at this that it embarrasses her. Okay, so anyway, it's hard to do. Okay, so here's Richard Feynman, who was the great physicist, okay, and who invented something really important, a theoretical physicist. And he was asked, he was also a very good teacher and very personable. He was asked by somebody to, he's writing all these, what does he do to his daily life? He stares at these data, and then he invents ingenious theories to explain them, okay? And he uses he's pushed quantum mechanics. Okay, so someone asked him, some reporter asked him, hey, tell me, I don't know any physics, tell me what a physicist does. Okay, so here's what Feynman said, and it's okay. So think about this. So here's what he says. He said, here's what I do. And he was kind of thinking about astronomy. He says, I'm like this. Think of somebody who's ignorant. He doesn't know what the rules of chess are, the game of chess. You can substitute Go if you want. I don't know what chess is. But what I do is I get to observe a part of one game of chess. So I see the two players and I see their moves, and I write down the data. So I see these two guys moving these boards. So those are my data. And then he says, from those data, I am asked to infer what the rules of the game of chess are. And then what he says is, well, that's what I do. He says, what a physicist does is he infers laws of nature from incomplete observations of physical system. that's a perfect description of what Ptolemy and those guys did. And for him, he was talking about how light behaves, okay? So that's what he says he does. So that's a metaphor. That's a metaphor. And notice he says rules of the game of chess. So look at this. So what's the relevance of that for economists or political scientists? So his metaphor, it's not a metaphor. It literally describes what a structural economic macroeconomist or statistician or structural microeconomist does. And what my colleagues do, what some of you do, from incomplete observations. What are observations fundamentally? They're about prices and quantities. An economic statistician wants to infer a game that generated those prices and quantities. So what's a game? So von Neumann and Morgenstern told us what a game is. We have a tight definition of a game. So the reason this is relevant, and of course, I'm sure Feynman had this in mind, but I'm betting you make you a bet. Feynman never read. He had contempt for economists. He probably never read von Neumann or Morgenstern. Okay, so I'm bad at this. Okay, what's a game? So von Neumann and Morgenstern and Nash gave us a definition of a game, and you could get my grandsons to know this because they play games. So what is it? It's four lists. It's four lists. It's a list of players. It's a list of the available choices for each player. It's a list of payoffs to every player in the game as a function of the choices that are made by all the players in the game. Think about pickup basketball, soccer, baseball. And it's a list of information sets, what I know. So it's those four lists. What I know when I decide, and what you know when you decide. It's a timing protocol. That's in the game, who chooses what when. And it's an equilibrium concept. And the ruling equilibrium concept is a Nash equilibrium. And what does that mean? So an equilibrium concept is a stability criterion. It is that the Nash equilibrium is each person in the game is making decisions that are the best that they can make given what everybody else does. So why is that an attractive stability concept? Because I don't want to change. And given that I don't want to change, you don't want to change. Cool. Okay, good. Okay, so I'd rather get questions. So the physics metaphors in economics. So von Neumann and Morgenstern and Koopmans, they describe two types of statistical models. Kepler stage models, they call those descriptive models with curve-fitting parameters. That's what I already told you about. And Newton stage. And what they meant by Newton stage, they upped the ante. Those are structural models with parameters that are invariants. They characterize physical invariants that are going to be the same if you make interventions. So, for example, if I change, this is what we want to do, and it's a noble enterprise. Which I want to ask: if you take an economy, given where we are, it's really tempted to follow it. You take an economy with the same kind of people, and they have the same purposes, but there's one big player called the government and it uses one set of rules. So, one set of rules is the complicated set of rules that are used in South Korea and the complicated set of rules that are in North Korea. And there's a bunch of parameters that are the same, and you want to know if you change those, that strategy, what's going to happen to the whole equilibrium. And the Newton stage, that can help you do that. And then I'm going to show you the following. There's Kepler's third law, and there's Newton's interpretation. I'm going to stop here. So let's stop here. So I could just apply this to a whole bunch of things. So here's one way you could apply this to. So I'm just going to repeat the same thing, but I'm going to change look, this is what the great mathematician and physicist Henri Poincaré said. Here's what he said. The art of mathematics is to give the same names to a whole bunch of different things. What are our favorite names? X and Y. So I have some equations with X and Y, but now I apply it in different situations, like the quadratic formula. So if you know Python programming, a Python class, it's what Poincaré said. You just change he calls it an instance. Okay, so anyway. So digital finance. What's new and what's old? We can apply everything that we're doing here, and we can study Bitcoin and all sorts of other stuff. So I'm done. Thanks for listening. Okay.
네, 감사합니다. 교수님의 연구와 고민 그리고 열정이 우리 고려대학교 연구자들에게 큰 영감으로 다가올 것이라고 생각이 됩니다. 감사합니다. 시간이 조금 예상보다 많이 흘러서요. 짧은 질문 한 두어 가지만 받도록 하겠습니다. 질의응답은 영어와 한국어가 다 가능하고요. 혹시 우리말로 질문을 하실 분들은 경제학과 어윤종 교수님께서 통역 도움을 주시도록 하겠습니다. 질문 있으신 분들은 손 들어주시고 마이크 전달해 드리겠습니다. 네, 저쪽부터 한번 시작해 보시죠.
Thank you for your lecture, Professor. My name is Claire. As someone, I think I am someone who are currently at the Kepler stage. And
Me too.
And I have a feeling that I can never move to the Newtonian stage. Never ever. So in my case, what personal effort should I make to advance to the Newtonian stage? And as a researcher, is what we need ultimately just time? Is it only through prolonged effort over a very long period that this transition is possible? Personally, from Kepler stage to Newtonian stage? Or should I accept that I might remain at the Kepler stage throughout my lifetime? This is my question.
Okay, it's a good question. So the answer is I don't know. But it's a challenging issue in statistics and machine learning all over the place. So here's what, and different people have different views of this. So I think the secret is to try to copy. So if the purpose is, first it's fine to stay at the Kepler stage, because finding patterns, look, I think science is a big team. So the guys who find patterns, that's really important in terms of setting the stage for other people who are maybe better at the Newton stage. But in terms of, if you ask kind of what the Newton stage people do, I just spent a long time studying the life work of Robert Lucas, who was a Newton stage person, or some people think he was. And what he did is he spent a lot of time studying things. He studied math and statistics, studied game theory, he studied it really hard, and years. And then you think you're getting nowhere, and then a miracle happens. That's the way it happens. So I think, and if you kind of ask, why did Newton get farther than other people? It's because he had studied things. He knew more math. And he had some instincts. He also, I think people that made big advances, they've read a lot and they've paid attention to what the people around him did. That inverse square law, that's not original with him. Somebody else was doing that. So he's kind of looking around and making connections. And then so your question's a great one. So it's like, how big is the gap between Kepler and Newton? But it's there. And like I've read, there's a great book on, so machine learning it's a huge area, and there's lots of salesmanship. There's a book by Michael Bronstein, who's a genius in a frontier thing, and he's basically telling you, if you ask the machine and the data to just tell you something by themselves, they're going to be completely silent. So like Junil Kim's advisor, Chris Simpson, you have to have a prior or a prejudice. It's an interaction with what you tell the machine to want to learn. And that's true in the Kepler stage, even in the Kepler stage, because remember, Kepler and the little model of what those guys were doing. They were looking at the same data that Ptolemy did, and they said, I can fit with fewer parameters. And that turned out to be a big advance. And if they hadn't done that, Newton wouldn't have had anything to work at. So I don't know. Great question. And my answer's terrible. But guess what? The thing about asking good questions is more important than getting good answers. Come back.
답변 감사합니다. 아까 이 앞에 질문하려고 손 들으셨던 분이 한 분 계셨던 것 같은데. 네, 좋습니다. 네. 마이크 좀 옮겨주세요.
First, thank you for your meaningful speech about economy and AI. Before to begin, I'm not sure that my question is related to the lecture, but this question is something that I've been most curious about since the advent of AI. I believe investors can profit when the market displays temporary inefficiencies, such as by discovering undervalued stocks or buying stocks during panic selling. But if AI were to make the market perpetually and completely efficient, then what's the difference between investing and gambling? If all available information is fully reflected in prices, then wouldn't investors have to rely entirely on luck?
Say the last sentence. Just say the last sentence.
Sorry. If all available information is fully reflected in prices, then wouldn't investors have to totally rely on luck? This is my question.
On luck, did you say?
Yeah, luck. Just luck.
Okay, so this is a great question, and I'm going to give maybe an even worse answer than I gave to the other one. So if you kind of ask, okay, here's what I like to do. Just because I'm really slow, I like to go think about kind of I like to take apart what you asked me. So use the term information and all available information. So if we think about that, what's the definition of information? So, it's a word that Shannon and Turing gave a tight definition. And what they said was, information is a surprise. That was their definition. Now, what did that mean? It was a surprise relative to, if it's something that you didn't anticipate, there's information. If something happened but you knew it was going to happen, that's not information. Okay, that was their definition. Okay, so now, how did they formalize that definition? And they used it. They invented this definition because they wanted to break codes in World War II and do other things. Okay, so I'm leading up to kind of an answer. I'm going to push back the question on you. So their definition of information, to make it concrete and something they could write equations for, they said, well, it's a surprise relative to a particular probability distribution. So in order for them to define information, they had to say, well, I know the probability distribution. I just don't know the information. And so a random variable comes in. I know its distribution. It comes in, and I can say how much information that is if you let me observe this random variable. So for them, information was about the content of a random variable. Okay, so now what's a random variable? It's something that obeys a probability distribution, which I know. Okay, so now the question is, if you look at models of asset pricing, and you're thinking that all available information is encoded in existing, in prices, according to whose model, probability distribution, do you and I have the same probability distribution when we're seeing data? So it turns out if you look at finance, a lot of part of there's a communism of models that we all know we're using the same probability distribution. And if we're in a situation in which you and I disagree about the probability distribution, then we disagree about what's a surprise. Okay, so that's why I don't know the answer to your question. And I think other people don't either. And now you asked really question. So what risk is I know the probability distribution. And I'm just taking draws from it. But if I don't know the probability distribution, that's what Frank Knight and other people called uncertainty. Knightian uncertainty. I don't know what the distribution is. Okay, and lots of so Knight and various other people think that that's a big part of what we have to cope with in life. My friend Chris Sims doesn't like this, partly because he doesn't like some of the implications. But so your question is right. So I can hold up my head with some dignity that I've given you a really bad answer to that one. But I was honest. Oh, and I'll tell you something. Actually, it's much better. It would have been a better use of your time. I apologize for this. If you watched the following video, because it illustrates, it's an answer to your question, and it's about, there's someone named Sebastian Jaimungal. He's not an economist. He's a statistician and a computer scientist. And what he does is he builds models of algorithmic trading. He's been doing this, he has a lab that does this at the University of Toronto. So what he does is he builds a model of a market, an artificial model of a market, and he uses statistics and machine learning in real time to trade. If you see his video, you'll see he uses every trick in the book beyond what I've done. He uses game theory. He uses something called mean field game. He uses deep neural nets. He uses deep Kalman filtering. He combines all these things, and he gets a smart agent who are trading against other smart agents. See, your question gets at this. Well, look, if I'm trading, you said all information's in prices. See, in his model, some of that's going on, but not everything. And he's actually looking at real data in real time. And that's frontier stuff. And but I think he's one of the people at the frontier, but he hasn't solved all the problems. And he can't just use machine learning. That's kind of the lesson. He's doing lots of the art of building economical models. It's beautiful. And you couldn't have done, you're going to be able to do things I could never do. It's all in Python too. Yeah, I'm done.
이제 사전트 교수님을 보내드려야 할 시간이 된 것 같습니다. 사전트 교수님이 오늘 다른 일정이 있으셔서 더 질문들이 있는 것 같긴 하지만 여기서 마무리해야 될 것 같습니다. 그리고 10년 혹은 20년 뒤에 여기 계신 학생 여러분들 중에 한 분이 100번째 혹은 200번째 넥스트 인텔리전스 포럼에 연사로 오시는 그날이 있기를 기대하면서 여기서 마치겠습니다. 감사합니다.